Hi, I am Dr. Derick Lindquist, and I am the Dean of the Jindal School of Psychology and Counseling. And I'm happy to welcome you to the new episode of Minding the Mind. Now, a primary goal of this series is to introduce our viewers to the biological side of psychology, i.e. behavioral neuroscience. In order to do that, we really need to have at least a rudimentary understanding of the brain and the way the neurons in the brain operate. With regard to the brain itself, it's not real big, right? It sits inside of your head. It's about 3 pounds on average, and that's usually about 2 to 3% of a person's overall body weight. But critically, that very small brain uses 20 to 25% of all the body's energy. So it really needs a lot of energy input in order to function correctly. Amazingly, the human brain contains 80 to 100 billion neurons, a tremendous number. And that's supported by what we call glia cells. They offer support, nutritional and otherwise, to the primary neurons. There's another 80 to 150 billion glia cells in the human brain. So again, amazingly complex. Now, I think most of you are aware that there's 2 hemispheres in the brain. So every structure in one hemisphere is going to be duplicated in the other. There's different ways that we can conceptualize the brain. One of these is we can talk about the lobes of the brain. There's actually 4 lobes, a frontal lobe in the front. We have parietal, occipital, temporal. Each of these lobes have different functions. And this is an idea that we'll talk about more later in the series. Today, my primary concern is to introduce and hopefully provide a basic understanding of neurons and their operation. So here's an actual image of some neurons in the brain. Over here we have a little cartoon. Now there's 4 different parts of a neuron that I want to go through today to help you understand. First, at the top of every neuron or nerve cell, we have what are called dendrites. Now these dendrites are kind of like these finger-like protrusions. And in fact, when you look at a single neuron, like over here on the right, you can see it's kind of like a tree-like structure. It branches. And so we refer to this as the dendritic tree. On each of the dendrites, each component of it, each branch, we have these little protrusions. These are called spines, and you can see one here in the yellow. These spines form the contact for all the connections between different neurons in the brain. And each neuron can have millions of these dendrites or dendritic spines associated with it. And what's cool is that they're really dynamic, right? Your brain's not static. It's not just there and never changing. It's actually being altered, updated, and modified moment to moment every day, day in and day out. So here's just an example. Over 12 hours, this is a real dendrite, and we can see changes. We have a spine that's grown here. We have another spine that's grown here, but it disappears by 8 hours later. So again, as you develop, as you experience the world, your brain is constantly being modified as a result. The second component is the actual cell body. This is where the DNA and your genes are located. Okay? Important, but we're not going to put a great deal of emphasis on it today. Rather, I want to talk about this third structure called the axon. The axon is the, quote, output of a neuron. And when we look at the axon, it has one primary function. It's responsible for the relay or propagation of action potentials. Now again, many of you probably heard this term. Have you ever heard people refer to as neurons firing or spiking? That's the idea. It means they're firing an action potential. An action potential is nothing more than a little electrical blip that travels down the axon into the tip. We call these axon terminals. Now, this is a little bit of a complicated story, but here's the gist. The inside of a neuron is electrically negative relative to the outside. What happens during an action potential is you have positively charged molecules. We call them ions. Those ions flow into the axon. That's what these little yellow squares here, the little plus sign. So as those positively charged ions flow in, that causes this electrical signal to propagate down the axon. It ultimately will invade the axon tip. But that's it. That is an action potential. Very similar to flipping a light switch and the light turns on. That's because of an electrical signal that's flowed through those wires. Now, to put this in sort of perspective and provide an actual application of this idea, if you've ever gone to the dentist right? He gives you an injection of Novocaine or lidocaine, and that's meant to block the pain. It's an anesthetic. Well, it does so by blocking the action potentials that are generated by the pain neurons in your mouth. By blocking the action potentials, that information can no longer be conveyed to the brain proper, and as a result, you do not actually experience the pain. Okay? So action potentials are critical to how neurons operate. We have 100 billion neurons, all of which are firing action potentials at various moments in time. And just as an aside, all of your neurons are firing action potentials. A very common idea that I hear repeatedly is we only use 10% of our brain. That is unequivocally false. Every neuron in your brain is activated at various points in time. So again, inherent in this is there's a lot of complexity. Now, final part here is the synapse. The synapse is the connection between one neuron and a second neuron. Okay? It's where they come together. So what we know is that of those 100 billion neurons, each neuron has tens of thousands to hundreds of thousands of synapses or connections. So what this means is that in the human brain, there's on the order of 125 trillion synapses, right? Just a mind-boggling number. So the human brain is truly the most complex structure that we know of in the universe. Now, why is this important? Because again, this is how neurons communicate with one another. So this is done through electrochemical communication. We've just talked about the action potential, which travels down into the axon terminal. That is the electrical part here. But that action potential leads to the release of a chemical, i.e. called a neurotransmitter from the axon tip. That is the chemical side. That neurotransmitter is released into the synapse itself, and ultimately it binds to what we call receptors on that secondary neuron. Okay? This is it. This is the way one neuron communicates with a second neuron. Now, neurotransmitter, maybe you've heard that term, maybe you haven't, but I assume most of you, I'm going to guess, are familiar at least with some of these. So if you've ever heard of dopamine or serotonin, right? These are classical neurotransmitters that are synthesized and released in the brain. So let's put this together. 100 billion neurons, 125 trillion synapses, all of them being activated at various moments in time, right? Again, tremendous amount of complexity. So for any single neuron is receiving thousands, maybe tens of thousands of inputs through these synapses at any moment. Now here's the idea. Is if that neuron is stimulated sufficiently, we call it excitation. If it's excited enough, it's going to go on and fire its own action potential. You can see that over here on the right. So one neuron fires an action potential. That excites a second neuron, which fires its own action potential, which can activate a third neuron, a fourth neuron, a fifth neuron, and so forth. This is the idea, right? It's fairly simple. I hope everyone can grasp this because this is how we operate as humans. Whether we're talking about your ability to move, your ability to sense the world, right? You can hear me and see me right now. Whether it's your own thoughts or desires or emotions. All of this is ultimately regulated through this neuronal communication in the brain. It's truly a remarkable phenomenon and a really interesting one at that. So I look forward to talking to you more and discussing the brain and its various functions moving forward.